Hello students, in this video we will be seeing data link layer protocols, a topic from Unit 2. Now we will see the protocols of data link layer. Traditionally, 4 protocols have been defined for the data link layer to deal with flow and error control. These 4 protocols are Simple Protocol, Stop and Wait Protocol, Go Back N Protocol and Selective Repeat Protocol. Although the first 2 protocols still are in the use at the data link layer, the last 2 have disappeared. We therefore briefly discuss the first 2 protocols here. For better understanding of this topic, we explain the working of protocols with the help of finite state machines. An FSM is thought of as a machine with a finite number of states. The machine is always in one of the state until an event occurs. Each event is associated with 2 reactions, that is, defining the list of actions to be performed and determining the next state. The first protocol is a simple protocol. We assume that this protocol doesn't have any flow control and error control. Also, the receiver can immediately handle any frame it receives. In other words, the receiver can never be overwhelmed with its incoming frames. Now we will see the working of simple protocol with the help of finite state machines. Each FSM has only one state, the ready state. The sending machine remains in the ready state until a request comes from the process in the network layer. When this event occurs, the sending machine encapsulates the message in a frame and sends it to the receiving machine. The receiving machine remains in the steady state, ready state until a frame arrives from the sending machine. When this event occurs, the receiving machine decapsulates the message out of the frame and delivers it to the process at the network layer. Here we see the flow diagram of a simple protocol. It is assumed that the sender is sending a packet in terms of frames to the receiver, and he imagined that the receiver will not send any acknowledgement to the sender, and he will keep on sending the packet without getting any interrupt. Our second protocol is called Stop and Wait Protocol, which uses both flow and error control. In this protocol, a sender sends one frame at a time and waits for an acknowledgement before sending the next one. To detect corrupted frame, we need to add a CRC, that is cyclic redundancy check, to each data frame. Now we will see the implementation of Stop and Wait Protocol with the use of FSM. It has sender states, ready state and blocking state. The sender is initially in the ready state, but it can move between the ready and blocking state. The next state is a ready state. When the sender is in this state, it is only waiting for a packet from the network layer. If the packet comes from the network layer, the sender creates a frame, saves a copy of the frame, starts the only timer and sends a frame. The sender then moves to the blocking state again. Next state is a blocking state. When the sender is in this state, 3 events can occur. If a timeout occurs, the sender resends the saved copy of the frame and restarts the timer. If a corrupted acknowledgement arrives, it is discarded. If the error-free acknowledgement arrives, the sender stops the timer and discards the saved copy of the frame. It is then moved to the ready state again. Here we see the finite state machine for the stop and wait protocol at the receiver end. The receiver is always in the ready state where 2 events may occur. If an error-free frame arrives, the message in this frame is delivered to the network layer and an acknowledgement is sent. If a corrupted frame arrives, the frame is discarded. Now we will see the working of stop and wait protocol with the help of flow diagram. In this diagram, we can see that the first frame is sent and it got acknowledged. The second frame is sent but it got lost. After timeout, it is again resent. The third frame is sent and acknowledged, but the acknowledgement is lost. The frame is again resent. However, there is a problem with this scheme. The network layer at the receiver side receives 2 copies of the third packet, which is not right. In the next section, we will see how we can correct this problem using the sequence number and the acknowledgement numbers. This flow diagram shows how to add sequence numbers and acknowledgement numbers to prevent duplicates. The first frame is sent and acknowledged. The second frame is sent but lost. After timeout, it is resent. The third frame is sent and acknowledged, but the acknowledgement is lost. The frame is resent. To avoid the problem, we add an acknowledgement number for each and every acknowledgement which is sent. Also, we will add a frame number for each and every frame is being sent. The two protocols we discussed in this section are designed for a unidirectional communication, in which data is flowing only in one direction, although the acknowledgement may travel in other direction. The protocols have been designed in the past to allow data to flow in both directions. However, to make communications more efficient, the data in one direction is piggybacked with the acknowledgement in the other direction. To make it more clear, piggybacking means adding frame numbers for each and every frame sent by the sender to the receiver. Also, adding acknowledgement number for each and every message which is sent by the receiver to the sender. Fine, we have come to the end of this topic. We will see the next topic in the next video. Thank you.